Oh well, I'll just point. Okay, cool. Great. So thank you all for coming. Today I'll talk about the result that I have with my advisor Venkateswamy that I announced in the speed talk on Wednesday. So let's get to it. So So our main codes of interest in this talk is going to be about locally correctable codes. So what are they? So throughout the talk, I'm just going to focus exclusively on binary linear codes and not like nonlinear or even like non-binary. It's just all about binary linear codes. So I'm going to look at binary linear codes of dimension k that is q-query locally correctable against a delta fraction of errors. So what does that mean? Is that suppose I have some code root c, which is zeros and ones, and I get some errors here. Also, the bits are supposed to flip, but yeah. And they get at most delta n adversarial errors. And I want to correct this index I. Just this index I, not the whole code word. And what I can do is I can just query q places at random, XOR the bits, and get to and recover I. And I can do that with a good chance of recovering it. Okay? Like say in chance like 70%. Okay. So our main question is if I given a linear code that's q query locally correctable, in other words, q delta LCC, how small can the block length n be in terms of the message length? Okay. And we already know some known results. We know that the Hadamard code is a 2-query LCC with 2 to the n, with n is equal to 2 to the k, and degree q minus 1 Reed-Muller codes is a q LCC with n is equal to 2 to the k 1 over q minus 1. Okay. And these are the best constructions that we know. And these constructions are basically folklore. It's kind of astonishing that these are the only things that we know. But I mean, is that really because we don't know any better constructions, or is there actually inherent lower bounds and are out there? Okay. So I want to recap some of the history that Peter gave a wonderful exposition of. So I'll be pretty brief about this. There was this era before 2022 where we had some exponential lower bounds for 2-query LCCs and some polynomial lower bounds for q-query LCCs. And in particular, we had a quadratic lower bound for 3-query LCCs, which was the same as the 4-query LCCs. So they weren't any different. And then there's this post-2022 era where there's this beautiful connection between locally decodable codes and semi-random CSP refutation. And from that, we were able to get a cubic lower bound for 3-query LCCs, and with some polylogarithmic improvements by HKMMS. And there's this recent wonderful breakthrough by Pravesh and Peter that got an exponential lower bound for 3-query linear LCCs with n is at least exponential of k of 1 over 8th, and n is at least exponential of k of 1 over 4th, improvements by Yankovitz more recently. So these are all the results before. And except for the works of Peter Pravesh and Tal, all lower bounds also work for the weaker notion of LDCs. Okay, they only correct the first k message bits. And furthermore, all these proofs, in some form or the other, in a formal sense, take a q-query LCC and reduce it down to a 2-query LDC. So it's some combinatorial code transformation from one code to another. And then once you do that transformation, you can apply a lower bound on this 2-query LDC, and then recover a lower bound for this q-query LCC. Okay. So our motivation in this work is, first of all, can we show that degree 2 Reed-Muller codes are optimal as binary linear 3 LCCs? In other words, can you show that this optimal bound of n is at least exponential of root k? Okay. The other thing is can you get a more direct proof that kind of gives a quote unquote deeper explanation of this exponential linear 3 LCC lower bound? I hope one day that there should be constructions of LCCs out there, and I would prefer that the lower bounds be more informative about what kind of LCC should look like at a deeper level, and that's one of the main motivations of this work. Another one. And obviously, there's this concrete motivation. Okay. So what do we show? Well, we show that any 3-query LCC satisfies the bound k is at most log squared n times log n. In other words, if you flip if you manipulate this equation around, you get the n is at least exponential of k to the exponential of root k over log k. So in comparison, degree 2 Reed-Muller is already optimal, right? It's n is equal to square root k, exponential of square root k. So it's almost there. And furthermore, our proof is rather short, modulo this big breakthrough by Alon, Bucić, Sauermann, Zakharov, and Zamir from around November last year on this rainbow cycle problem. But it's a rather different technique that just goes directly improves lower bounds for 3 LCCs. And I should also mention that the progression P to have an independent work that get the exact bound of like exponential root k for these so-called linear design TLCCs via like a reduction from TLCCs to TLDCs. Okay.
Time for this.
Well, yeah, it's kind of a coincidence. There was also a lot of works before, which I'll show before. But I mean, like, yeah, I'll talk about this in the end a little bit. I think a few of the people who were working in the area kind of knew about this problem, but it didn't have any direct implications. Like there was an easier problem that you could easily solve instead. Okay. So we also have a second result, which is that actually we can get improved lower bounds for Q delta LCCs, binary linear, for Q odd, and they satisfy this bound, like omega tilde of like k to the q minus 1 over q minus b. So it just improves the polynomial exponent a little bit better. Okay. For comparison, the previous bounds for Q odd for Q LCCs were n is at least k to the q plus 1 over q minus 1. And these fractions are a little bit like hard to look at. And so for simplicity, you can look at 5 LCCs. We get a quadratic lower bound for them. And for comparison, before we knew that 5 LCCs had a bound of omega tilde of k to the 3/2. Yeah. And the second result just follows by like viewing our work as sort of a generalizing our work into some sort of reduction from Q LCC lower bounds to Q minus 1 rainbow LDC lower bounds, and then applying these known reductions for Q LDCs to 2 LDCs. So our result follows immediately from the following theorem. If I give you any fixed constant delta, if I take the dual code of a 3-query LCC, then it has a coupling radius of log n times log n. So what does that mean? It means that if I take all the dual code words in space, so all these blue dots represent like dual code words, and I take a radius of like log n times log n around each one, they cover the entire space. Okay, you can kind of see it's very dense because it's like a very short radius. Okay. And by a simple counting argument, you can get the main result that we have. So you have like 2 to the n minus k code words in C perp. They cover all 2 to the n code words in F2 to the n with Hamming ball of radius log n times log n. So by a simple counting argument, like the right hand side is like all the number of code words that they cover, and 2 to the n is the whole space. So by simple like calculations, we immediately get the lower bound that we have. Any questions so far? So this result is inspired by a work of Iceland and Samorodnitsky, who proved like a similar result for 2 LCCs with a covering radius of just delta inverse, so basically O of 1. And we sort of refine, like reinterpret their works and generalize it to 3 LCCs and combine it with the rainbow LDC or this rainbow cycle problem. In combination with that. So for our proof, like we take a different outlook at this statement. So this looks like a very geometric statement, but in fact, like we look at it in a more combinatorial way. So what does that mean? It means I fix a generating matrix M, and I take the rows of the generating matrix V1 to Vn, each Vi is length k, and this theorem can be equivalently stated as the follows: if I give you any x in F2 to the k, I can find a very small set I of size like log n times log n, such that x is actually a sum of these row vectors Vi. So every Vi can be written as a very sparse sum of the rows of the generating matrix of this 3 LCC. Okay. And why is this true? This follows on the fact that M transpose is the paracheck matrix of C perp. So let's just see how that works. Yes, columns are code words. Yeah. Oh, sorry. Yeah. Yeah. So if I pick any W in F2 to the n, I can just take its like syndrome, which is x is equal to M transpose W. Then because by this theorem, I can write x as like a sparse sum of the rows of the rows of M. So that means I can find a very sparse vector E with very small weight, at most log n times log n, such that M transpose is equal to x. Okay. So by some simple algebraic manipulations, M transpose of W plus E is equal to 0, and so therefore W plus E is in C perp. Okay. That's the equivalent way of looking at the problem in a rather more conventional way. And for comparison, if you look at degree 2 Reed-Muller codes, the bound is just log n for this statement. Okay, and this follows from like a very very simple fact that if I take any m by m matrix, where you think of m as roughly being square root of k, it's the sum of at most rank 1 matrices. Okay, so in some sense, you can kind of see what kind of makes degree 2 Reed-Muller codes a bit special, because each row of the generating matrix of Reed-Muller code is a rank 1 matrix or a sketch of a rank 1 matrix. Like this bound or this bound? Oh, the first one. Oh, this one.
Yeah,
Oh, this equivalence. This equivalence holds for any codes.
Yeah. No. 3 queries.
Oh, for 3 queries.
Why the first theorem breaks for?
Oh, the theorem breaks. Oh, because so we're gonna use the rainbow cycle problem to prove this bound, but we don't have the way we apply rainbow cycles really depends on the fact that we use 3 queries. For more general ones, we have to use this general thing called rainbow LCC lower bounds. Which, I'm not sure if I can get into in the end. Yeah. But you can get also covering radius upper bounds too for the general thing. By reduction. It's just going to be it's going to be n to the 1 minus 2 over q minus 1 in this case. Some one factors. Okay. So now it suffices for us to prove this theorem, and we're going to do this by reducing the problem to this rainbow cycle problem that I mentioned previously. Okay. So let me just go in deeper into this rainbow cycle problem, what it is. Okay. So I have a graph G, like any usual graph, and I have n vertices in it, an average degree d bar, and I say that G has a proper edge coloring. So what does that mean? So I take all the edges and I color them with given colors, but I have this property that has to be proper. What does that mean? It means that if I take any two edges, E1, E2, that are incident to the same vertex, then they have to have different colors. There are 2 different ways you can look at this. If you look at any vertex, all the edges incident to it have different colors. That's one way to look at it. The other way to look at it is that if you look at any color class of edges, it's a matching in the graph. Okay. So the question in this area is, how large does the average degree have to be in terms of the number of vertices to guarantee that G has a rainbow cycle? So that's the basic question. It's a generalization of the classical problem of or the classical result, the classical fact that any graph with at least n edges has has some cycle in it. Okay.
Rainbow means you see all the colors.
Oh, right. So rainbow, what does a rainbow mean? It means that, so for example, if I take this thickened edges around here, this triangle, it means that no edge color repeats in this cycle. That's what it formally means. So there's a very simple lower bound of d bar is at least log 2n, and this follows on the basic fact, just by looking at the hypercube, and you color each edge based on the direction that it goes. Okay, and the reason why this has no rainbow cycle is because if you have any second hypercube, whenever you go up, you have to go down, so you have to repeat that any color edge twice. Okay, that's the only lower bound we know about this rainbow cycle problem, more or less, asymptotically. Okay, now in terms of upper bound, there's been a lot of works since 2007 by Kothari and Manohar, Bucić, who introduced the problem, and then there's been some very recent developments in the last 3-4 years on this problem, culminating in this work by Alon, Bucić, Sauermann, Zakharov, and Zamir, getting all the way to the almost to the lower bound that we know of log n. Okay. So these are wonderful works with many different techniques. Introduces some new technique called homomorphism counting along the way. Among those techniques, there's another technique that's similar to some region growing argument that this recent work uses. It's a very beautiful results in this area. I should also mention that should someone prove a tight d bar at most O of log n bound for this problem, by our reduction we immediately get a tight lower bound of exponential root k for this problem. So in fact, it's just down to this last log n in this problem. If they can get it, then we can get a tight result for all binary linear LCCs. So any questions so far? This is all the statements that I wanted to say, and now I'll get into more of the proof.
So I guess all of this works for binary alphabets. Could you define a generalization of rainbow cycle that would work for a larger alphabet?
Yeah, so we tried the generalization. It somehow doesn't work.
So, yeah,
the pluses and minuses don't work out for some reason. Yeah, so it's funny. Yeah. Okay, so let's get into some proofs. So let's just start with a formal definition of binary linear LCCs. So I give you a Q LCC with generating matrix M, has rows V1 to V2 to Vn. What does it mean to be a binary linear LCC? It means that you have n hypergraphs h1 to hn over vertices n, such that the two following properties hold. H1 is a Q uniform matching with HI's at least delta n. It's supposed to be Q uniform instead of 3 uniform. And for any index I and any hyperedge in HI, we have the property that the row vector VI is the sum of the Q row vectors VA1 to VAQ. Yeah. It's a more like this is a very specific way of looking at the definition of the LCCs for the linear case, and especially even for binary. Okay, so it has a very clean statement in that sense. Okay. So just some terminology. I say the hypergraph is Q uniform if every set in it has size exactly Q for any A in the hypergraph. And it's a matching if any two sets have disjoint support. Yeah. And I should mention that this definition is independent of any choice of generating matrix of C. So whether I picked another generating matrix and defined it, is going to be equivalent because any generating matrix is equivalent to any other generating matrix by like a basis change. Okay. So I did say our works are inspired by this Iceland and Samorodnitsky work. So I'm going to give you a reinterpreted argument of their work for two LCCs, and it's going to really inspire how we're going to go about proving two LCCs. Okay. So I fix a two LCC C with the generating matrix M as before, and now for any x, because the VI is span F2 to the K, then I can write x in as a sum of VI1, VI2 to VIT. Okay. Now here's my claim. If t is at least 5 over delta, then I can shrink the sum in some way. Okay? I can find another sum that sort of shrinks it in size. Okay. And if I can prove this argument, then like by iteratively doing it, I can conclude that the covering radius is a O of delta inverse, or a O of like 5 over delta. Exactly. So it suffices for us to prove this claim. Okay. So how are we going to do this? We're going to pick a uniformly random index j. And now we're going to observe the following. Fix for any index I that I pick, if there exists a j1 in n for which j0 and j1 are a edge in the matching hi, then vj0 plus vi is equal to vj1. Right? This follows from the definition of a 2 LCC. Okay. And since hi is at least delta n and j0 is just uniformly random, then this occurs with probability at least 2 delta. Okay. Otherwise, I just set j1 equal to j0, and then I just simply have the vj0 plus vi is just vi plus vj1. This is just like vacuously true, you could say. So I should also mention that because j0 is uniform, then j1 is also going to be uniform too. Okay. So now I have everything set up. And what am I going to do? Now just write x as the same thing as before, but I'm going to add a vj0 plus vj0 at the beginning of it. Now here's what I'm going to do. I'm going to take the second vj0, and I'm just going to sweep it from left to right using these identities that I wrote before, the first one here and the second one there. Okay. And every time I do this, either I can lose a vi, and it just disappears, or the vi stays. Okay. Either that happens or that happens, and because of our previous argument that this vi disappears with probability at least 2 delta, means that each vi will stay with probability at most 1 minus 2 delta. Note that whenever we sweep, we go from a uniformly random index to another uniformly random index, so we can keep iteratively doing this. Okay. And just by looking at the expectation of this new sum, it's going to be at most 2 plus 1 minus 2 delta of t, because each vi has a chance of 1 minus 2 delta of staying. That's less than t. And that finishes the argument. Okay. So it's a very simple, very nice argument of Iceland and Samorodnitsky, and it's quite rather short. Although I should mention that we interpret this proof in a very different way. The original proof involved like looking at it looking at the graph, some K graph as a discrete manifold and analyzing its discrete Kothari curvature and applying the Bonnet-Myers argument. I should mention that argument is this Kothari curvature is somewhat similar to the path company arguments if you've seen before in sampling. Okay. That's a reinterpretation of their argument. Now, okay, so we see this argument before, and now we're like, okay, let's just try to do the same thing. Let's just take some sum and just take some vi randomly with a random index and just sweep it from left to right. What happens? So we fix an index I, pick A in a form of random, and probably at least the delta, we can find some indexes B and C and N, such that VA plus, this should be ABC is equal to ABC is in HI, such that VA plus VI is equal to VB plus VC. Now, okay, if you can do this sweeping, that's fine. You can have a good chance of doing that, but it doesn't shrink the sum as we did before. But that's fine, because it also doesn't blow up the sum too. So you don't really do anything. You just move from one place to another. It's not doing the same thing. It's not doing much, but you have a good chance of like moving around from one pair to another pair. Okay. And again, I already see why dequeries is very crucial here, because if it was 4 queries or 5 queries, every switch that we do will incur an additional cost, and we increase the length by 1 or by 2 or 3 or so on. But in 3, it always stays the same thing. Okay. So how do we play this this so-called swapping game, right? We just take some index A, some index I, and then we just swap it for like B and C. Okay, and we keep doing these swaps every now and then until we somehow miraculously get 2 indices, and because we're over F2, we get some cancellation and we shrink our sum. Okay. So now we have this original sum. We added some index Vj and Vj at the beginning, and now we want to do this swapping game. We want to forget the first index and play with the second index and do some swaps until we get some cancellation. Okay. Even like before shrinking, you need like 2 cancellations to get a shrink because you added Vj plus Vj. But can we at least when we add this new index, can we at least even produce a meaningful cancellation in any form or whatsoever? Like we ask like a very simpler question. Can we get any sort of cancellation that we can get our hands on? And the second thing is can you even find any starting index j? I don't need j to be even random, uniform random. I just want any index j that could work, that could get some cancellation. I'm asking a very, very simple question of whether this whole approach could work in the most simplest case. Okay? And we can already start seeing that this problem is getting a little bit more combinatorial here. So what is this swapping game? I give you some input Vj plus Vi1 to Vi2 to Vit and some starting index j. And now we can perform these rules like Va plus Vi is equal to Vb plus Vc for any I and n and ABC and Hi. Now they play this game with these moves. Now your goal is to obtain two copies of the same index and therefore get a cancellation. Okay. So it's some weak version of what we eventually want to get to. And I want to set some ground rules because how do you play this game? There's a lot of things you could do, but you need to be careful about how you do these swaps. Okay. The first rule is that unlike in the 2 LCC case, any winning strategy should be kind of Markovian, quote unquote. In other words, when you start playing this swapping game, you already know where you want to end up at. Okay, you already look ahead and you're like, okay, I want to reach that that index in 2 different ways and get a cancellation. Okay. This is kind of important because you can't, if your approach was Markovian, then how can it tell between a path of length log n versus a path of length O of 1? So you really need to distinguish between these 2 cases, and having a Markovian strategy does not seem to be able to distinguish that. Okay. So in other words, we just want to look ahead about how we're going to get this cancellation. Okay, I'll say more about this a bit in the next slide. The other thing is I can't really rely on any local checks beyond the indices that I currently have. I can only rely on these hypergraphs hi1, hi2, and all the way to hit, and not on any other local checks. The reason is because you have these vi1s, vi2s to vits, and you want to use them somehow. So the only way you can use them is to sort of use their local checks in some form or the other. So you kind of have to do them. You kind of have to use them in some form or the other. And the third thing is from each hypergraph, you can only use at most 1 local check from it. Because once you do a swap with VIT, it's gone. You don't know if it will ever come back or in any way or another, so we can only guarantee they can use it once. So you only have that budget of using any local check once. So I have these ground rules. And what do we want to do? We want to, as I mentioned in the first ground rule, we want to use this you want to use some non-Markovian winning strategy. So what can we do? How can we develop this non-Markovian winning strategy? And the best thing is just just draw a graph, okay, and just see what this graph looks like, and use some properties about it to look ahead and figure out where we want to go. Okay? So I want to particularly construct a edge color graph. So I'm going to consider a graph over n, and for each s and t from the indices and each hyperedge ABC, I'm going to place a monochromatic triangle of color s in this thing. So what do I mean by this? So I have n vertices here. What I'm going to do is I'm going to put one color here with a bunch of red triangles. I'm going to put another set of triangles, blue ones, and green triangles, the third one, and then some yellow triangles all around. And now, like, you have all these, like, this very complicated graph. And now, what's the swapping game going to look like? Is that you start from index j, and then you perform a swap with color 1. You get 2 new indices, and you have to keep track of the fact that you use color 1 at j. So you can't use the red color again at any time later. Okay, and then I use the color 3 at the index b. So I lose b, but then I get indices b1 to b2. So all the purple, nodes with the purple circle around them are ones that are active. They're still in the sum. Okay. And I'm treating the indices as like colors. So I'm like not hoping for a cancellation with the indices that I currently have. Okay. So this is how the swapping game kind of looks like now. So what do I want to do with this thing, with this very nuanced graph? Okay. My goal in the end is to get 2 purple circles to coincide by using each color at most once. So I'm hoping to do some use the colors in one way or another, and eventually just get 2 purple circles on the same node in some way. No, we stay at the same length. So we haven't shrunk it. We asked for a simple question, just get any form of cancellation. So if I go back, slide here. Okay. So when we had the sum of length t, we had 2 indices, j and j. So that increased the length by 2. So we need actually at least 2 cancellations. Before I even ask you that, let me just ask a simple question. Can we get any cancellation in the first place?
And every time you do a step, you're in fact increasing the size.
No, because we're in a 3 LCC, the length stays exactly the same. And that's the most crucial property about 3 LCCs. If it was 4 LCCs, every step increases the length by 1. Yeah. In 2 LCCs, every step actually shrinks the length by 1. So actually, in 2 LCCs, you just have to do some arbitrary moves in some way or another. If you do enough moves, you have shrunk it by a lot.
So now all those moves that we did, we kept the size exactly the same. And if we ever get 2 purple circles to collide, then we shrunk it by 1.
We shrunk it back. We shrunk it. So we started from t. We added these 2 auxiliary nodes, indices vj and vj. That increased the length from t to t plus 2.
Now we need 2 cancellations.
We need 2 cancellations. Well, let's just get 1 in the first place. So now we are playing this game on this edge color graph. We're trying to come up with some way to get these 2 purple circles on the same thing. Okay. So this graph is pretty complicated. I just took some triangles and I plunked them down on some graph somewhere or another. What can I say about this thick graph? Okay. It turns out that if you can take this graph and delete 2 edges for each triangle, it gets a lot simpler. I just deleted 2 edges from each triangle. Now it looks like a much nicer graph. It has some isolated vertices, but that's fine. But now, because each AI is at least delta n, well, first of all, because I deleted 2 edges from each triangle and the triangles were already disjoint, then this is a property edge color graph. Okay. Furthermore, because each AI has at least delta n edges, then each edge color class has at least delta n edges. So in total, this graph is supposed to have a lot of edges in it. Okay. And because t is at least log n times log n, this graph is going to have at least n times log n times log n, okay? Because you have log n times log n colors, and each color class of edges has at least n edges, give or take. So because of this, we can actually use the result of Alon, Bucić, Sauermann, Zakharov, and Zamir, and find the rainbow cycle, which is conspicuously right there, right? So I'm just gonna thicken the edges of the rainbow cycle, and you can kind of see where it is. T is the length of the path that we started off with. So we had the sum vi1 to vit. T is the length of that thing. So now with this rainbow cycle, we could win this so-called swapping game. How do we do this? Okay. So we went back to this very complicated graph, but now I thicken the edges so I can see where the rainbow cycle is at. Now here's what I'm going to do. I'm going to set the starting index to be the vertex opposite to any edge of the rainbow cycle. So it was this original j that we started off with, and it's opposite to this to this edge in this monochromatic triangle. That's where j is. Now, like you can kind of see, like I'll just like dynamically show you how we win this game. So we do use the first color to get these two nodes right here, and then I'm just going to do the following. We use the second color to get that to get these two new nodes, and then I'm going to forget about the one on the leftmost, and the one I'm going to focus on the one at the bottom, and I'm just going to keep walking around the cycle until I end back here. And that's how we get. That's how we win this like swapping game. So I went through this like crazy like like swapping game, reducing down to some very very simple problem. But what's the point of like reducing down to this problem is that okay, once we have a very simple, we end up with this very simple statement that actually what we completely did was just actually start from sum. We got some cancellation, and now we ended up with a different sum of the same length. So we just like moved our sum from one thing to another. That's literally what we just did. We added two new indices, and then we just deleted one, so we've gone back to the same length. So what was all that for? We haven't even shrunk our sum yet, but let's just slowly upgrade our like statement to something that's even stronger. Okay, but first let me prove this statement formally because I just gave a rough sketch of it. So by a previous argument, what we can get some indices j1 to jm, and hyperedges as, bs, cs in each hypergraph hjs, such that we have this rainbow cycle property that the last index of this hyperedge is equal to the second one from the next hyperedge. Okay, and this holds for every index s and m. So then we have the following: we start our initial sum, and then we just split off the indices that have like the rainbow cycle associated to them, and we leave out the rest. And then we just substitute the local checks for these VJSs. So we have VAS plus VBS plus VCS. So let's just isolate the VBS and VCS on one side and leave the VAS on the other side. And because this is a rainbow cycle, we get a cancellation. So we've gone back to a new sum. Okay, so that's the whole thing. So we just went from one sum to the other, but actually we can actually get something stronger. So this is some existential result. We went from one sum to the other. We moved around a little bit, but actually we can upgrade this a little bit. We can say something more about what the indices vi prime to vit prime are. Okay. So in fact, we can say the following. If you take, it's the same statement, but now I can give you the additional property that the indices vis, all the possibilities of vis is at least some delta over 2 times n. So you can get a lot of different indices when there are many different shifts that collectively cover at least a constant fraction of all the indices that you could ever hope for. Okay. And this follows by a very simple fact. It's the same argument, but instead of taking the original hypergraphs hi, we just take all the hypergraphs hi prime that avoid like some collection of indices, some w. Okay, as long as w is at most delta over 2 times n, the same argument goes through. So we can just simply upgrade our lemma from the first one to the second one. So we went from this existential argument to some statistical statement, and now what can we say? This fact corresponds to the fact that this swapping game they started with not only has one winning starting node, but it has like a constant fraction of winning starting nodes at the beginning. Now we can finish the argument from the previous slide. So we start with any x, write it as a sum of the vi's for some subset I, and I can do that because the vi's span f2 to the k. Now the claim is if I is larger than delta inverse times log n times log n, we can shrink this sum. Much like the same way the Iceland and Samorodnitsky argument went through, now it's going to be a bit more combinatorial. So I'm going to take my set I, I'm going to partition it into some constant fraction of blocks, I1 to IP of the same size. Now, because of how large I is, each block IL has size like delta inverse times log n times log n for each L and P. So by previous lemma, we can shift each IP into some other sum. And moreover, the shifts of each like IP covers at least like some delta over 2 times n indices in n. Thus, the shifts, like if you look at all the shifts collectively, they cover at least like 2 n indices. But that can't be like, what does that mean? It means that there's like I can find 2 shifts I prime L1, I prime, like I can find 2 indices L1, L2, and shifts I L1 prime and I L2 prime, so that these 2 shifts actually intersect at one point. Okay. So far, I've not increased the length in this sum in any way yet. Okay. So using these true shifts, we end up with a new cancellation because when I substitute IL1 with IL1 prime and IL2 with IL2 prime, we're going to have two new sums, but they'll have a common index in between them. And because we're over F2, these two indices are going to cancel. So we get a new sum of length at most like I over 2. That's the whole argument. Wait, what?
You added the IJ and IJ?
Yes. Oh, I added this, like, are we talking about the VJ and VJ that I added at the beginning? I added those, but then it got canceled. So I got this like new shifting argument. Yeah. And this proof overview is not in the paper because it's kind of long. But this shifting lemma is there. Yeah. This is just how we ended up with the proof, this intuition of the swapping game. So that finishes the whole argument for our 3 LCC lower bound. That's pretty much it. Now I'm going to talk a little bit briefly about how we do this, how we get the second result for higher query LCCs. And it turns out that a mean result is a more specific instance of a general reduction. So we have these binary linear QLCC lower bounds you want to get, and it turns out we can get those from these so-called like rainbow linear, binary linear rainbow Q-1 LDC lower bounds. These lower bounds are sort of in a formal sense a stronger form of lower bounds than usual LDC lower bounds. These can be a bit it turns out that these formally prove usual binary linear Q-1 LDC lower bounds. Now the most important thing is that actually we're going from Q-1 LDC lower bounds to QLCC lower bounds. So the query complexity drops by 1. So in our original proof is actually a reduction from rainbow 2 LDC lower bounds to 3 LCC lower bounds. Because for rainbow 2 LDC lower bounds, we can interpret this result of ABSZZ and as a rainbow 2 LDC lower bound. Okay. So it turns out that actually, if you interpret this ABSZZ result as a rainbow 2 LDC lower bound, and you take like this Q, take this classical Q-1 LDC to 2 LDC transformations that people have done before, then you can actually, it turns out that these preserve rainbow cycles between the 2 LDCs. So if you replace the usual 2 LDC lower bounds with this rainbow 2 LDC lower bound of ABSZZ, then you actually upgrade all these like Q-1 LDC lower bounds for Q odd to rainbow ones, like almost no cost. Okay, okay. So rainbow LDC. Okay, a rainbow LDC does not entail an actual LDC. It's just like it's very similar to how LDC lower bounds go. Yes, it's about the matchings only, and not about any code. Yeah. So if you want to get, I'll just mention briefly, so I think I have a little bit more time. If you have, so a LDC lower bounds corresponds to finding hyper edges, for which some such that these edges, when you XOR them, they become 0, and some color appears an odd number of times. In rainbow, you want a collection of edges so that each color does not repeat. Each color appears at most once, and the XOR to 0. So that formula is stronger than like the usual binary linear LDC lower bounds. Yeah.
So because you have like LDCs of large alphabet, so it doesn't work for large alphabet reductions, right?
It works for fields of characteristic too, but not other characteristics.
So only two.
Only 2. Yeah. One of the problems. Yeah. It'd be interesting. Like one of the few restrictions is just like this thing only works for characteristic 2. So is there any way to extend it to arbitrary finite fields? We tried, but something very tricky about how to make these like the signs work. We tried it like for at least a solid month, but we just don't know how to make it work at all.
I'm right. There is like as characteristic goes up, our constructions also become worse and worse if you want to insist of being linear, right?
What's that?
I'm saying the constructions that we know are like worse when your characteristics goes up. It's not that you can get better constructions from high characteristics.
I believe so. Yeah.
Stay the same.
There's also another simple question. Is there a way you can get this cubic 3 LDC lower bound and therefore a cubic lower bound for binary linear for LCCs. So it turns out that this reduction from 3 LDCs to 2 LDCs that we did I did with Peter, Pravesh, and Venkat somehow just doesn't really work for like rainbow 3 LDC lower bounds. So because somehow like it disrupts the way the color classes operate. So it'd be really interesting to make that work. Now, this is the most interesting question: do better LCCs exist for Q at least 4? Which is like very obvious, but I am like very hopeful that someday there should be some LCCs out there better than Reed-Muller. That's all. Thank you.
So regarding the other question of dropping the linearity requirement, any insights on that?
Oh, the linearity requirement. Well, we don't know how to remove it. But also, like even the exponential lower bounds of Peter and Pravesh and Tal also like don't also work for linear only. Peter has some recent work to also get some improved lower bounds for non-linear LCCs. Yeah. So as far as we know, that's the only thing we know. The reason, at a high level, it's because even if you look at these like 2 LCC lower bounds for large alphabets, it's somehow you're taking a lot of local checks and stringing them together. And every time you do that for like non-linear, it incurs a cost of epsilon. Because you're chaining so many things together, the cost is so like large, so you can't do it. For the LDC ones, you only chain like 1 or 2 things, so it's like, it doesn't cost that much. Yeah.
Is there any resemblance between the other proof and the proof of the combinatorial result?
Is there a similarity?
Any resemblance between the proof of other proof of the PLC lower bound?
Yes. Yeah. So the comparison is that both have the common trait of like they use chains, chaining in some way. You take some local checks and you combine them in some form or the other. But the way you implement this is a little different. And the works of Peter, like Peter Pravesh, and also in the work of Tal, you consider like a super polynomial collection of local checks. You want to make sure that these checks you decompose them into hypergraph decompositions. You want to make sure that one of these hypergraph decompositions is like well spread. So these chains are like a good distribution of hyper edges of like large of size polylog n. Another thing we just want to make sure that our result is some sort of extreme combinatorial argument. Extreme combinatorial rules that saying that if you have these hyper edges, you can sort of like chain them together to get some like cyclical chain, or like a bicycle one. So the figure in our graph we have 2 like cyclical chains and we XOR them at one point. That's really what the core of our proof is.
That's right.
Thanks everyone, all the participants.